Okay, now you've seen the part of speech tag. Let's look at the next step in processing. So now we can go towards a more syntactic analysis of a sentence. And the two main approaches you can apply here are either chunking or parsing. Parsing, you've probably seen or heard about. This is where you build a kind of parse tree, which tells you the grammatical structure of a sentence. So to be able to parse it, you need first a sentence, second, you need a parser, and then you need a grammar for the parser and typically also a lexicon. So to be able to find out what is the subject, the verb, the object, and so on. Chunking is a bit simpler than parsing. You don't try to build a complete tree. You just try to group some words together into something like a noun phrase or a verb group. So very often it's problematic to do parsing. I'll talk about different parsing methods in a minute, but if you want to produce a syntactic parse tree and the sentence isn't complete, not grammatically correct, if it has new words that don't exist in the dictionary, or you have a mistake earlier on, in tokenization, in the sentence splits, and the part of speech tags, then the parsing can fail or produce not so useful results. So what you can still do in cases like this is do chunking, meaning grouping some words together. And one example is building these NPs, these noun phrases. Basically, you look at the part of speech tag, you identify the so-called head noun, which can be a normal noun, a proper noun, or a pronoun. And then you can have modifier. So in English, typically adjectives and determiner. So these three words here, tagged as DT, JJ, and NN, would be chunked, would be grouped together as a noun phrase. And this is something that can be done relatively reliably, even with a rule-based system. Well, there are a number of ingredients that can go into a noun phrase. Every noun phrase must have a head noun. So like in the example here, the head noun is dog, and in the NP here, the head noun is, well, there's only one word, the pronoun we. So this is the head noun. And then there are different grammar rules for English. Yeah, you can have an optional determiner, one or multiple modifiers, and a mandatory head. So this is again similar to regular expressions. Here showing it in Gate. Remember, when you run it in a document, the regular expression run on the graph, and then you can chunk these words together. So here, all the green ones are highlighted noun phrases. So how do you do it in Spacy? So again, we have Spacy, we load our language model, we get an NLP pipeline, and this default pipeline already has a chunker built in. So again, we are processing a document, autonomous cars shift insurance liability towards manufacturers. Before, what we processed from the document is the tokens, but this pipeline also produces these noun chunks. So for each noun chunk, we are printing out the text, as well as we print out the text of the root word, the text of the head, and the dependency type. So for the text autonomous cars, the head, the root is cars. For insurance liability, it's liability, and for manufacturers, there's only one word, it's manufacturers. So in many applications, these chunks are surprisingly useful. Earlier, we talked about named entity recognition. Yeah, entity like persons, locations, also companies, patents, and biomedical documents, things like organisms or proteins, they are also named entities. And with this chunk, we already group together all the words that we need. And then we can run an additional machine learning tool that gives us the type for it. We'll talk about this a bit later on when we come to named entity recognition. What is still missing if we just have chunks is the relations between them. Very often we want a deeper analysis. We don't just want the entity. We also want to know what are the relationships between the entities. If there is an invention in a document, we want to know who invented it. When there is talk about a product that has problems, we want to know which company is mentioned together with that product. When we process biomedical documents, we want to know which organism produced this protein. So for finding these relationships, we need a deeper analysis, and this is where parsing comes in. So parsing, again, in natural language processing is quite difficult because there are so many ambiguities. And I'll just show you two typical problems briefly. One is the problem of PP attachment, where PP is the part of speech tag for a prepositional phrase. So if you look at these two sentences here, he ate spaghetti with a fork, he ate spaghetti with tomato sauce, you can see that the preposition with a fork and with tomato sauce has to be interpreted completely differently. In this case here, what he is eating is spaghetti with tomato sauce. But in the first sentence, he is not eating spaghetti with a fork. Yeah, that would mean he would be eating the fork, which is, well, not so healthy, I suppose. And if you look online, these are just two examples of half a dozen similar examples that all have the exact same beginning. He ate spaghetti with, he ate spaghetti with a friend, he ate spaghetti with hunger. The syntactic structure is always the same, but the way you have to parse the sentence, where you have to attach this phrase, you attach it to he, you attach it to ate, you attach it to spaghetti, is different. So this is extremely difficult to find the proper attachment. Another problem is when you have multiple nouns together, it's not clear what the noun boundaries are. This is the so-called NP bracketing problem. So if you look at this phrase here, plastic cat food can cover, well, one way you can read it is that there is a cover for cat food that's in a can, and this cover is made out of plastic. This is the most likely understanding of this phrase. But if you run this through a system, you can see that you can interpret this in dozens of different ways. It could be a plastic cat or plastic cat food. Plastic cat food that can cover something else. There are lots of different ways of grouping this together. And again, it's quite difficult in general to find out what's the correct solution. So again, spaCy has a parser built in. So when you run this on a document like here, Apple is looking at buying UK startup. You've already seen earlier when you print out the tokens, you get out not just a part of speech tags, you also get these so-called dependencies between the tokens. And this is one way of representing a parse tree. Basically, there are two different ways. One is called a constituent-based parse tree, and the other is called a dependency-based parse tree. So this classical version here is probably the one that you've seen before. You have something like a grammar. Sentence consists of noun phrase and verb phrase. Verb phrase consists of verb and NP. NP can be pronoun or determiner a noun, and so on. So you have a grammar, then you process the sentence with part of speech tags, and you try to come up with this tree here. A dependency-based parse tree looks different. Again, it's a tree, but now we are building the tree just based on the words, and we're recording dependency between the words. So we have the root of the sentence, the verb here, prefer, and you can see it has a subject and an object. And then again, we record the dependencies from the object, which is this noun, and it has a modifier and a determiner. So in practice, in modern systems, this is the typical representation that you see more often because it's a bit more robust first, and you can directly take this representation and read information out of it, for example, for information extraction or question answering. Whereas here, this, if you want to extract certain information, it needs further processing. And second, if you have a kind of, if you have a sentence that doesn't conform to the grammar, this fails more easily than this kind of method. Very often you don't deal with sentences that are perfect. You have sentences, if you process social media posts, Twitter, they are not grammatically well-formed sentences. So most likely your proper English grammar will fail to build a parse tree out of it. But you can still get at least some dependencies between the words. So this can be done a bit more reliably than this kind of parsing. So try this out, produce some parse trees using the next task on the worksheet, and I'll see you back for the next part.